Question B3, this question is about radioactive decay. So we're actually going to be using these formulas over here in dealing with this, and we'll define a couple of those as we go along. So we have nitrogen 13, is an isotope that is used in medical diagnosis. The decay constant of nitrogen 13 is 1.2 times 10 to the negative 3 per second. So the decay constant is this over here, is your lambda. That is your decay constant, and that is equal to 1.2 times 10 to the negative 3 per second. Now it says over there, it asks the question, define the decay constant. Now the decay constant is defined as the probability, so it's the probability that a nucleus will decay in a unit of time. Will decay in a unit of time. So here we have 1.2 times 10 to the negative 3 per second. So the probability is this over here, is 1.2 times 10 to the negative 3, or you could put that into a decimal value. Per second is the probability that a nucleus will decay. So the question goes on, it says a sample of nitrogen 13 has an initial activity. Now your activity, this is your A, and so it has an A, what we would call our A0, initial activity of 800 BQ, and this is Becquerel, and this is the number of radioactive decays per second. So it means that every second 800 nuclei are decaying. The sample cannot be used for diagnosis purposes if its activity becomes less than 150 Becquerel. Determine the time it takes for the activity of the sample to fall to 150. So your initial activity is 800, and then your final activity is equal to 150. So over a period of time, it's going to fall to the point where it's going to be 150 decays per second. Now we're actually going to be using this formula over here, and I'm just going to explain it a little bit more detail. Let me just write it up over here. So we're going to get A, our activity, is equal to lambda n0 e to the minus lambda t. Now this lambda n0 is actually your activity at time is equal to 0, because this is the probability that one will decay, and this is the number of particles that are available. So this actually gives you activity. So we could write this as, sorry, not as A0 is equal to A0e minus lambda t. And we see we've actually got that, we've got that, and we just need to find our t. So we're going to get 150 is equal to 800 times E, that's your, and this is your lambda is equal to 1.2 times 10 to the negative 3 times your time. So we're going to calculate this. We're going to need to use our calculator. So obviously we'll divide the 100 and divide it by 800, and we'll get that, so it's 150 divided by 800, and we get 0.1875 is equal to E minus 1.2 times 10 to the negative 3t. And then what we're going to do, and this is especially important for those that are taking studies, we're going to put this into our log form. And so we're going to get that the ln, or the log to the base e, of 0.1875 will equal minus 1.2 times 10 to the negative 3t. So I'm going to divide both sides here. I will divide both sides by 1.2 times 10 to the negative 3. We don't have to worry about the negative sign. That will come into play later on. That's not important. So 1.2 times 10 to the negative 3 going to divide by both of those, and I'll get my t. So this is you'll see this button on your calculator. It's the ln button. So we take ln and we type in that number 0.1875, and we get that value, and we're going to divide it by 1.2 exponent -3, and you'll see your value there is a negative value, but because you divided it by a negative, it actually becomes positive. So your time, now this time will be in seconds, will be 1395 seconds. So if we do that in seconds, and we can divide that by 60 if we require, but we get about that. Now you see here that you're given all of these to two significant figures, one significant figure. So I could write that as 1400 seconds would be correct there. Alright, so we've got that. And then we are going to do the last question. Let me just bring this up. Then it says calculate the half-life of nitrogen 13. Well, that's pretty straightforward. We don't need to do any calculations. We can just use that formula over here, that your half-life is equal to the ln of 2 divided by your 1.2 times 10 to the -3. So we just do that straight into our calculator. Just calculate that out. So we get ln of 2 close brackets divided by 1.2 exponent -3, and you get about 577, 578, and we can round that down to about 580 seconds would be your half-life. Then going over the page, outline how the half-life of a sample of nitrogen 13 can be measured in the laboratory. So going on to this one over here, outline how the half-life of a sample of nitrogen 14 can be determined in the laboratory. So what we can do is we can just measure the activity. So you just measure the activity, and because it's got a relatively short half-life, it's about 10 minutes, 580 seconds, about 10 minutes. You can measure the activity. So what you would do is you can plot a graph like this, your activity against time, and you would measure your first activity at time is equal to 0, and then you would measure it as it goes down. And from this curve, every time, if this is activity 0, you would find when your activity goes to activity over 2, that time over there would be your half-life, t to the half. And then nitrogen 13 undergoes beta decay. Outline the experimental evidence that suggests that another particle, the neutrino, is also emitted in this decay. So it forms beta positive decay. Outline the experimental evidence that supports that another particle is emitted at that time. Well, the beta positive decay is continuous. It's not discrete. The energies are not discrete, as with, say, your alpha decay, alpha and gamma decay. And so therefore there must be another, I'll just go up here, therefore there must be another particle that takes away the balance of the energy. That takes away the balance of the energy.